I'd like to begin by saying that I'm one of those people who have had the fortune of being associated with Blue Waters as a user almost since the beginning. So I thought I would give a talk that try to summarize some of the highlights from my experience since the early 2010. Okay. So I've listed a number of NSF grants that allow us to use the machine, and the names of my collaborators. I'd like to say that the Blue Waters team has been very helpful, and here are the names of 4 PhD students who graduated within this period of time, and there's one other student now currently you have to move on to some of the other machines. Well, what is turbulence? I'd like to show the cover of a book that reveals the history of a study of turbulent flows. And turbulence can sometimes be very difficult, and you can see here, the sky was pretty dark, great contrast with what we have here. And in the picture, there are a number of people who are probably in fear for their lives. And so why is turbulence so difficult and so dangerous in a situation like that? Because of order disorder. And we have this here's a visualization produced from data computed on Blue Waters. And so I would say that we have had a rewarding journey. Sometimes we were nervous. Sometimes we were nervous about whether the results were actually correct. Sometimes we were worried about whether the codes were being too slow. But thanks to the staff on Blue Waters, we have done pretty well, I would think. We had the first PRAC grant from NSF in 2009. We had access to the machines in the middle of 2012, almost exactly 9 years ago. Well, I'm sorry, 7 years ago. And so we have conducted some high-risk solution simulations that allow us to address some difficult questions. We've learned some lessons in both the science as well as the computing. But as I said, I think in the end we have turned out okay. And so what are the properties of turbulence? We would be particularly interested in the disorderly fluctuations over a wide range of scales, many degrees of freedom. In other words, turbulence is pervasive in many branches of science and engineering, astrophysics, mechanical engineering, aerospace engineering, atmospheric science, and all of that. In many cases, the flow is characterized by a high Reynolds number. And what is the meaning of the Reynolds number? I would say the best way of looking at it is that we have a wide range of scales that increases as the power of the Reynolds number. Numerical simulation often the best source for detailed information. Experimentalists, they have a real flow in the lab, but the question is, can they measure everything? Can they calculate, can they obtain everything to the degree of detail that we are capable of doing using the approach of the numerical simulation? So turbulence is, I would argue, that has always been a grand challenge problem in computing. The flow is three-dimensional, unsteady. We have to divide up the data. We have to deal with communication. Every step up in the problem size. Whenever you want to double degree spacing, and you want to double degree spacing in every direction, then you get an 8 times increase in the number of grid points. So that's why sometimes you will recognize, as you'll see here, it takes a number of years for people to go up one step, 4096 in this direction, 8192 cube, and also something bigger right now. So what has Blue Waters enabled for us? We have focused on the relatively simple turbulent flow, unlike the last 3 talks with important problems concerning turbulent boundary layers. Now we have isotropic turbulence. So we just focus on a disorder. We say that we think about a disorder as statistically the same in every direction. We have a Reynolds number based on the Petascale. And we have the largest production one, 8192 cube. We use 256K parallel processors. In fact, the same number of nodes, the same number of cores on the Blue Waters machine. We also took advantage of some special opportunities to perform some simulations at 12K cube and 16K cube. The last one has a resolution of 4 trillion grid points. And of course, this consumes hundreds of millions of core hours, and also we have a 2.5 petabyte near non-storage accumulated, and we try to see what we can do with that for the purpose of some future investigations. And here there's a quick overview of some of the topics where we have produced the publications. Some of the publications are on the algorithm, CPC, computer physics and communication, as some of you may know. And so let's look at turbulence. The equations that we solve are the three-dimensional Navier-Stokes equations, conservation of mass and momentum. And on the right-hand side, all the forces acting on the fluid. And we have a periodic domain. So we are staying away purposely from all the solid boundaries. Imagine that I'm not just looking at the turbulence somewhere in this space here. Okay. So I can simplify the boundary conditions for my convenience. And we just like typically we would use the Fourier decomposition. And then we would transform the entire equation to Fourier space or wave number space, where we have this equation, which is simpler to deal with. First of all, in fact, it becomes an ordinary differential equation. The main challenge is how do we compute the Fourier transform of these products of the nonlinear terms. Mathematically, if we want to accept result, then will be a convolution integral. Cool cost will be proportional to n to the power 6, which is of course not feasible. So we use n cube. We get n cube log n if we want to perform the multiplication in physical space first, and then we transform back and forth. And because of all of these transforms, the three FFTs are very important to us, and they are also important to other domain science communities. And then we go to our parallel computing. The first thing is how do we divide up the data to make the 3D FFTs not so painful? And because we want to use a very large number of MPI processors, so we will have to come up with different ways of dividing up the data in a way that will allow us to go beyond n parallel processors. So we have a 2D domain decomposition. We have row and column communicators. If the data were decomposed like the one picture on the left, we will take FFT in this direction. About FFT in the other direction, then you have to do the transpose. And basically, we need to redivide the data along different directions. And the transpose involves all-to-all communication, and also because the data before the communication is not in contiguous memory areas, so we do need to do the local packing as well as the unpacking. So the communication intensive nature is our greatest challenge. So how do we make the code communicate more efficiently? First, we could consider trying to reduce communication overhead by using fewer MPI processors. This may not necessarily lead to a reduction in overall war time because the message size also increased. And then we could also see if we can do a non-blocking all-to-all. While communication is going on, can something else also been going on? So that's the idea of overlapping. May be possible with OpenMP, but it was not possible with the earlier versions of OpenMP, I would say. And also, overlapping may not be very effective if the two operations to be overlapped are not taking anywhere near the same amount of time. If communication is 9 times taking let's say 9 times more longer than computation, then there's not much that we can get from doing the overlapping. But works on blue waters very well. It's the idea of remote memory addressing using Fortran core arrays, and that was well supported by the Cray compiler. So basically, we are doing one-sided communication. We imagine that if we can send a message to somebody's brain, and that person will automatically react without worrying about. We don't have to worry about whether that person has time to read our emails or not. So that is the idea. So we can declare some major buffers at core arrays. Core arrays are arrays that are accessible to other processors, and it requires some extension to the Fortran standard. So all we do is one-sided gap. There's no put involved at all. And we are grateful to Bob Frieder, who was on the Blue Waters team early, and then someone with Cray, he actually figured out everything for us as far as this go away implementation was concerned. The other thing that was the problem for us was that because the code was still doing a lot of communication tends to be sensitive to contention, contention from other jobs. So but the Bluewater staff was very willing to set up a reserve partition for us, so that would cut out all the network traffic, and we found out that the performance would improve substantially. And later on, in fact, that led to the adoption of topological scheduling on the machine. This is an old slide. Before, in the early days of Bluewaters, performance was very highly variable. These are essentially wall time per step, and the excess is a number of time steps. And so sometimes it goes really up here. For example, this was a pretty bad one. But if everything were ideal, under ideal condition, we actually got slightly below 9 seconds per time step, which is this dotted line. So this was some data collected over a period of several months, so eventually we got to a pretty good place as far as the performance was concerned. The IGO was pretty good. Then in addition to computing the velocity field, we also were interested in tracking Fourier particles. That's one of the reasons why turbulence is important. If you think about pollutants, think about subparticles in a flame, even some form of bioterrorism these days. If you think of a small piece of the fluid, where is it going to go? First thing, we have to know what this velocity, but we can obtain the velocity based on the instantaneous particle position, and also the knowledge of the order velocity of the velocity field and all the grid points. We use cubic spline interpolation with some advantages in terms of accuracy as well as the differentiability in time for the velocity. But it was not easy to track hundreds of millions of Fourier particles. And so at one time it was a little bit lost. So my former student and I at that time, we made a trip up to the Bennett Champlain. We had a very good discussion with some of the staff members. So we eventually, after a while, we came up with the idea that we could change the mapping between the MPI task and the particles in a way to minimize the accumulation cost, and we were able to publish a paper. We also used the ideas of coaways to allow the cubic spline coefficients to be computed relatively quickly. So this is some performance about the particle tracking. On the left-hand side is the time required to compute the cubic spline coefficient as a function of the number of MPI processes. And grid resolution 2K, 4K, and 8K, and the scaling is just about what we could expect, somewhat similar to three-dimensional FFTs. And then there was some surprise here on the right-hand side, where we find that the data points in red referring to 8192 cube, they are actually scaling better than 2048 cube and 4096 cube. So somehow on a larger problem, our scalability actually improves. And that requires some explanation. We wrote this into a paper. Basically, this depends on the communication. The communication depends on the number of particles within two grid spacings of a subdomain boundary. The thing about interpolation is that you need information from neighboring grid lines. And so when you come to the boundary between one subdomain and another subdomain held by different MPI processors, there are some tricky things happening. And that will require some communication. But if the communication cost is actually proportional to the number of particles, then we will follow that. The data would be on this straight line of slope -1 on log scales. And there are other things that we can do about Fourier particles, but I think I don't really have time to talk about it. I can go back to this during the questioning period if that's the case. And the other thing about our work on Bluewaters is that we actually spend a lot of time studying the characteristics of so-called extreme events. Extreme events are events that are way out of the ordinary. If you have some random variable and you can, Thank you. And if you have samples that are 10,000 times the mean, well, this is 1,000. What about 10,000? Do we believe it? And why would it happen? And those are the questions that would come up. Right? And also, what are the effects of this on other aspects of turbulence? For example, if you have a flame, if you have a combustion, if you have a flame surface, if the flame surface were like something elastic, if you pull it out, then the combustion naturally stops. So that's why part of the reason, some of the reason why this is important. And we compute the three-dimensional local averages here because of they have a strong role in the theory of turbulence. And this is something that Bob Sidney helped us produce. We took a single snapshot, a 16K cube, and then we computed the local averages, and the local averages over dimensions of 1 grid spacing, 2, 4, 8, and so forth. And from a very highly wrinkled appearance, we get something very smooth. Of course, this is what we would expect. And a summary of our Blue Waters experience, I think we have made some advances in the domain science of turbulence, involving extreme events, dispersion, and also turbulent mixing. We have faced and overcome, to some extent, some of the challenges in the scalability. And we actually produced 3 papers based on the algorithms. Now, the data management, that is still remaining a challenge for us. We have 2.5 petabytes. We have on-site transfers in progress. So we'd like to be able to compress the data so that when we transfer the data to another system, external to NCSA, then life will be easier for us on the other systems in the future as well. Well, we're not done, although unfortunately our time on Blue Waters is essentially up. But we are not done in terms of the science. We still want to do more. Then we have to we have to use other machines. We have a dream of doing 32K cube. That certainly would require an exascale machine. So we have to get ready. We can use, but we can have many reasons for not being satisfied yet because so many problems about turbulence allow simulation can be used for actually a lot of very different purposes. For a wider range of scales, resolving the small scales better, longer simulations, so forth. And what about if we add some other physical effects, buoyancy in the ocean, magnetic fields, and also rotation? All of these lead to additional forces acting on the fluid in the state of turbulent flow. Very quickly, of course, this is a listing of the journal publications that we have produced. I think the very last one is still in review. And I'd like to thank the Blue Waters project team again. I would say that everybody we encountered have been very professional, very helpful. In particular, we interacted the most with some of the current and former members of the Blue Waters team here. I would say that if some of them did not go out of their way to help us, there would have been much less for me to talk about. Thank you very much.